It's pleasure and honor to have Professor Sergey Oblezin, professor at BIMSA, today, who is going to talk about spherical functions and mirror symmetry.
Thank you very much for introduction. I would like to, first of all, say that I am very thankful, and it's great pleasure and honor for me to join the faculty of BIMSA and to give talk here. So actually, I have moved like more than 2 months, and it is my great pleasure to give talk and to be part of the faculty. So thank you very much. I'm very thankful for Professor Yao. And, in my talk, I will comment on some way of research in maths in the recent decades. I would say probably even like 70 years, and just show a bit what my contribution and my points at this. So let me start with observations that number theory, you know, it is a part of maths which you meet number theoretic problems often quite unexpectedly doing other areas of maths, or even, well, it is well known in coding and cryptography in computer science. But of course, not all areas of maths are listed here where you meet number theory. And I remember myself when I was student at second year and studying group theory, and some statement was proven by methods of number theory. So like you use area that you are not supposed to use, but it appears like that quite often in maths. So the other point is that number theory is known to be a source of quite difficult problems, and that are long-standing, like Fermat theorem or Goldbach conjecture. So that it's, in this side, you can say it's one of the most difficult areas of maths. Probably people working in other areas will disagree and feel jealous. But I mean, I just want to emphasize in which sense I mean what it is difficult for me, at least, like when I was studying it at university. So it is often counterintuitive. So you pose a simple question like about some prime numbers or natural numbers, and then it appears that this question is very hard to answer, and probably even it becomes long-standing open conjectures for centuries. And this situation is contrary to, for example, geometry, where I mean classical geometry. So when you just have your model, geometric model, and you have some human intuition. So if you do consider this geometric object, it might be difficult to solve, but this one should be easy. So, but again, this is my personal evaluation. So mainly the point that I would like to state here, that in number theory, there is, it has been like a long, most of research in number theory was looking for pathways of transferring geometric methods and constructions, exploiting symmetry of problems in number theory. And mathematical physics is well known to be one of areas which is source of geometric constructions. That's why my research, and of course it's not only mine, it has been developed for many mathematicians for many years. So transfer geometric constructions from mathematical physics to number theory and apply to problems of number theory, and using the group theory and theory of symmetries. So this is like a motivation of the project. And now I come more specifically in a way how you do, because mathematical physics and number theory are huge areas. And like more specifically, another point is that also for centuries, theory of special functions has been well known to be a source of remarkable insights and hidden symmetries, sometimes mysterious ones, so that mathematicians, when trying to understand these symmetries, they came to some better understanding in areas like, for example, in mathematical physics, and same happens in number theory. So when you meet some special function, you see its symmetry, some nice properties, you try to find meaning of these symmetries and properties, and this leads you to some progress and just understanding those symmetries. So in this way, that comes the group theory as a background or layer, as a rigorous way to describe symmetries. That's why you can look at this into these terms, like that there are special functions possessing certain symmetries that appear in mathematical physics and number theory, and you may want to use group theory to interpret or understand them. In particular, for some special functions, you, in order to describe and understand rigorously these symmetries, you can interpret those special functions as functions on some algebraic structure, and in particular on Lie groups. And this comes to the notion of spherical functions. So spherical functions, they are functions on algebraic structures, most specifically on Lie groups, but it can be put in a bit wider context. But here I just want to again bring to your attention this logic that sometimes you may succeed in interpreting some special function. I will give examples later in my talk, just interpreting them, identifying with certain functions on algebraic structures, on groups. So this logic was pursued, as I mentioned, like 70 years ago. I could mention lots of names, but I think the two fathers of this approach is Harishchandra, mathematicians who worked in Princeton in US, and at the same time it was by Israel Gelfand, who was working in Moscow and then moved to US. So they were developing this theory of spherical functions and use it as a bridge between mathematical physics and number theory. So, you know, Harishchandra was originally a student of Dirac and came from like mathematical physics, quantum physics, and Israel Gelfand also was, of course, during all his career, very much influenced by constructions of quantum physics. So, as I said, after them, there was lots of excellent mathematicians pursuing these directions and working. I just won't list all of them. And let me notice I used pictures from the open sources just from Google. So it is like public pictures. Now, my specifically project, so that out of this huge area of mathematical physics, on the left side of the diagram, I used mainly two parts. So one is mirror symmetry, which comes from string theory, and the other is quantum integrability, which is an area which appeared like end of 60s, beginning of 70s, and have been developing also intensively since that time, and has a lot of connections with representation theory and theory of spherical functions. And on the right side of number theory, I would specify the Langlands program, which is again a collection. It's like a long-standing approach. It's supposed to be prominent and efficient in applying representation theory methods and also methods of harmonic analysis to problems of number theory, understanding better the number theoretic constructions. So this is like project that I'm working on, and of course, and there are many people doing this. So let me start with example of probably one of simplest special functions that probably most of you have met. So we start with combinatorial function like factorial that you meet when you just count chances, and then you want to extend it to arbitrary non-integer real numbers, positive real numbers. So you write down the difference equation, this one, yes, and with this initial condition. And so the solution appears to be a special function, and there is a integral representation, this integral formula discovered by Euler. That's why I put his picture on the top right corner. And then there is also a symmetry of this function that is a functional equation of the gamma function, so that you can express gamma function, product of two gamma functions via the periodic sine function, trigonometric one. So this function it can be interpreted in terms of it appears a lot in number theory and in Langlands program. So this is the way how it appears. So if you consider the Riemann zeta function, and then to study its symmetries of Riemann zeta function, mainly the symmetry is this functional equation. But the point is that the Riemann zeta function doesn't satisfy itself this equation, but only after you normalize it, multiply by the gamma function. After you do it, your so-called completed zeta function start satisfying the functional equation. And then once you multiply your zeta function by this gamma factor, you notice then there is another observation that original zeta function can be factorized into infinite product over all prime numbers. And so you just interpret this gamma factor that you add to get a nice symmetry equation as a one more factor similar to primes. So this is the how gamma factors appears in number theory and plays very important role, absolutely crucial. So second, I want to show how gamma function appears in the group theory. So you consider group of these 2x2 matrices just with two independent parameters A, B, where A is positive real and B is arbitrary real. And then you notice that each such matrix can be factorized uniquely into a product of diagonal and this triangular matrix. So in this, after this, you consider space of all functions on those matrices satisfying certain properties with respect to this factorization of matrices. And this is an infinite dimensional space of all functions. And you make your group act in this space. So to each such 2x2 matrix, you associate operator TAB, which just acts on each function. And then if you calculate the operator or matrix element of this operator, so how this operator acts in this infinite dimensional space, you obtain the gamma function. So that's how gamma function appears in group theory. And of course, it is probably there is nothing in common with the previous slides in number theory. So it's absolutely not obvious how these two are related. And so you see, even for such a simple special function, which is widely used, its theory and studying its symmetries is quite deep. And so then I come to a mirror symmetry. I won't describe the details, but just tell you as a statement that there are two integral representations for the gamma function can be found. So one is, in fact, it is Euler's original integral representation, but after some change of variables. And then this integral representation can be interpreted in terms of some string theory sigma model on a two-dimensional disk. I won't explain the details, just it is essential to know that the gamma function, the geometry behind it is some functions on a disk. And the other integral representation, like the mirror symmetric one, it is integral over infinite dimensional space, like on the previous slide, but it is a slightly different space. And so there is these two theories behind them are mirror symmetric and give explicit example of the mirror symmetry on the disk. And so give rise to two integral representations for the same special function. So this is how you can try to see in the simplest case. So now I will go to a slightly more difficult special function, but again, many of you could see it. It is widely known. It is Bessel function. And we'll again see how it works with a Bessel function. So it is called Whittaker function. It is a special solution to the Bessel equation, second order differential equation. And the group theory part corresponds to the function on this group of all 2x2 matrices. So you have 4 parameters. The mirror symmetry, so geometry behind it, is again maps on a disk, but to the 2-sphere, to the Riemann sphere, which is a union of 2 disks topologically. And the integral representation for the Whittaker function has this form where you have 2 gamma function and then a kind of Fourier transform of this product. So product of 2 gamma functions has a key meaning ingredient in number theory in the Langlands program. And each gamma function, as we have seen, is a theory on a disk. And the whole Whittaker function, the integral representation, appears to be a theory on a union of the 2 disks. So you glue together two disks and get a sphere. So remarkably, this you might get some idea how this works. And so here works like group theory intuition and topological intuition comes into help, because if you remember, the gamma function is a function on a group 2 by 2 matrices with two parameters A, B, and Whittaker function, you have a group of 2 by 2 matrices with all 4 parameters, and you use two gamma functions to describe it. So the further directions of the project, they come, of course, as you can guess easily to guess, to multivariable generalization of this picture. So you want to extend this understanding and this construction to special functions, to spherical functions in depending on more variables. Well, like considering functions on 3 by 3 matrices, 4 by 4 for arbitrary matrices. And so this gives multivariable generalization of this approach. Again, this is, of course, there are not only technical difficulties, it is a difficult, very difficult project. And each ingredient for the Whittaker function that we have here, 1, 2, 3, 4, generalizes in the following way. So Whittaker function is a special solution to the Bessel equation. Then you, in general, you interpret Bessel equation as a Hamiltonian differential operator of a quantum integrable system. And in general case, you expect to study wave functions, so eigenfunctions of some more involved quantum integrable systems, so eigenfunction of certain commuting differential operators that are Hamiltonians. So for the mirror symmetry, so it is disk maps of disk into two sphere or Riemann sphere. They come to mirror symmetry on flag manifolds in the Strominger-Yau-Zaslav approach, in the sense that you consider mirror symmetry on the target space, so on the flag manifold. And then, so functions on a 2 by 2 matrices, as of course generalizes to functions on n times n matrices or other classical groups like orthogonal and symplectic matrices. And in the Langlands theory, yeah, so it has more applications. Of course, as I said, these products of gamma factors and Whittaker functions, their generalizations play crucial role there. So at the end of my talk, I would like to introduce a kind of not answer, but it is like new direction, new perspective. So new perspective, which is supposed to be, expected to be, n variable generalization, like an answer. So what kind of answer we should study? At least check whether it works or not. It is the so-called Gelfand-Kapranov-Zelivinsky systems that were introduced like 30 years ago, approximately. So it is absolutely combinatorial data. So the initial data for which you define the system of equations that I show on next slide, it is just an integer matrix. So it is a rectangular matrix with integer entries, which encodes the combinatorics underlying it. And then you find another matrix, rectangular, satisfying these properties, so like orthogonality condition that one matrix times another transposed is the zero matrix. You get like a dual matrix. And then using this combinatorial data, you define this, at first glance, scary system of differential difference equations. So equations 1 and 3 are difference, and 2 and 4 are, 1 and 3 are differential, and 2 and 4 are difference equations. And so Gelfand and Graev proved that this system is holonomic, which means that this scary system actually has finite dimensional space of solutions. So it is nice in this sense. And I would like to give you just 2 simple examples of these systems and solutions. So when we take this matrix to be 1-by-1 matrix, when the 4 equations degenerate just to these 2, so one is differential and one is difference. And difference equation appears to be exactly the equation of the gamma function. And the solution, in the simplest case of the Gelfand-Kapranov-Zelinsky structure, you reproduce the gamma function that we have started with our talk as a simplest example. Yes, that it is independent of U. Yes. Well, gamma function is known not to be solution of any differential equation. So, yeah. And the second example, when you have again a differential equation and difference equation, and the solution is given below, which is like an integrand function of gamma function. So these 2 give simplest examples of the GKZ so-called system, and of course, yeah. So in our recent paper, we have shown that Whittaker function, even for GLN n times n matrices, can be fit in this system as well. So the current project, like new perspective of how we plan to pursue this, is to first try to describe what we know about mirror symmetry and quantum integrable systems within these GKZ structures, these combinatorial data, and then apply it to the theory of spherical functions to some group objects, and again to extract new constructions in the theory of spherical functions and representation theory, and then apply to the Langlands program. So this is like the plan for the project that I am working on and plan to work in the next years. So thank you very much, and please, if you have any questions, ask.
Questions?
Nikolai.
This Langlands program that you mentioned and these Gelfand-Kapranov-Zelinsky functions, what is known about the loop group analog for this?
This I don't know to my best knowledge.
What is known about the loop group analog of this? Because so far all your Lie groups were finite dimensional.
Yes, yes, exactly. So Gelfand and Graev, I think Gelfand, Graev, and with Reta later, there is a series of papers. They were within this construction. They proposed the case define so-called like QT gamma functions that are, appearing in extension of this construction combinatorial data, which again, one might expect to build up a link to loop groups. But again, to my best knowledge, nobody checked this.
More questions?
You said something about the Archimedean Langlands correspondence. Can you please elaborate on what you meant by that? You said as a further direction.
Well, I mean that it is just answering in brief that here you can see product of gamma to gamma functions. So this is a local Archimedean L factor for the automorphic representation of GL2. So for GLN Whittaker function, it's similar. So mainly you can see you can study Archimedean local L factors and Rankin-Selberg L factor studying Whittaker function. Yes. So the point, let me say like this. So for the original idea, which is in the Jacques Langlands book, that so originally Langlands formulated correspondence in terms of L factors. And the meaning of L factors, I mean, invariant meaning is like obscure, at least it's difficult. So instead, it was suggested that in that book, that already then it was suggested that it is instead of L functions, you can study local correspondence studying Whittaker functions that are matrix coefficients on groups, because it is clear what subject is. And so then it is later, of course, there is in non-Archimedean case, it was Kasselman-Shalaika formula that can be seen like local Langlands correspondence. Then in Archimedean, so yeah, there was, I mean, long activity in this, but it is in this direction.
So here, what is the A side and the B side?
Better go here. So here, A side, it is infinite dimensional integral, and B side is the finite dimensional integral, because the theory there just reduces to this, to finite dimensional integral, and this function here, W, it is like superpotential. So it is just, we interpret the in the Euler's integral representation as a superpotential. So the similar two integral representations found for Whittaker function. And this here, I write this integral representation, it is A side. And B side for Whittaker function, for GL2 Whittaker function, will be also like e to the power with superpotential. It is Givental's formula for GLN Whittaker function. So Givental in 1994 discovered this formula, and mainly it was a starting point of our project trying to understand group theory meaning of Givental's calculation.
And this has a similar generalization to N flat manifold.
Yes.
Factor.
Yeah.
Your spherical functions are exactly what Rafa will call the asymmetric limit of the brane amplitudes, which are special functions, classical ones. But the real interesting special functions are not the limit, the full function. So can you say something about the full function, not the infinite limit, which is quote unquote trivial?
Well, I think this is beyond my expertise. Yeah, so it is, yeah. So I think but I mean, better not comment about amplitudes. Yeah.
More questions? Yeah.
Thank you so much for the talk. You constructed a GKZ system as differential difference equations, and you interpret functions that over Archimedean groups as solutions to that. may I ask, is there any analog of this theory to like non-Archimedean case, or like specifically any relation with Kasuma-Shalika or non-Archimedean fields?
Yes. So for this is the point is that after Gelfand-Greif, they introduced this system of equations, and in symmetric form, like two differential, two difference. And then they wrote several papers. So first, generalized writing like a system of a finite field, because it is just combinatorial data of integral matrices. And then they had a paper like how it could be done over arbitrary field. But again, to my best knowledge, nobody looked into it, and I think it is a just topic of separate research. Yeah.
More questions? One more.
Sorry, I just want to ask, what's the criteria for this for the GG system to be holomorphic?
I mean, they are holonomic.
Yeah, yes. Are there any criteria for it to be holomorphic, or they just solve it, they find that they, I mean, fortunately to be holomorphic?
Yes, it is. My understanding, they, in fact, it was a very long-term project by Gelfand with collaborators, who was working during 80s for, I don't know, at least 10 years, and then continued. So my understanding, they were trying to find a system which would be holonomic.
Okay.
So that's what they were looking for, a system with a finite dimensional space of solutions.
Okay, thanks.
More questions? This is a great talk, you see. This is an indication of a good talk.
Okay, first of all, I don't really understand your talk, but I would like to ask two questions. The first one is that, do you see any non-Archimedean analog of your story? This is the first question. The second question is, so do you see the possible connection with your approach and the recent relative Langlands duality proposed by Bensby and the psychologist Langlands?
Oh, yeah. Okay. Yes, so it is like after the lecturer asks, are there any questions? And one student says, where I can find the book where it is written clearly. So it is the non-Archimedean I partially answered. So the local Langlands duality and some parts of this picture for the Whittaker function, I mentioned Kasselman-Shalika formula. So it matches to, can be matched into this, but of course, over periodic, over non-Archimedean case, there are, I mean, problems, of course, with mirror symmetry, with the geometric background behind it. And in this sense, I think, well, at least for me, for my project, I work with my student of a finite field case. I think it's first understand the case of the residue field before going through. Yeah, because, but for, again, for non-Archimedean, there are some hints, but you do, I mean, for mirror symmetry, it's missing. Yes. And for relative, well, yes, you can, again, you can, because the GKZ system, again, at least claimed to be well-defined. At least there are hints in Gelfand-Greif Retach paper studying it over arbitrary fields. So again, in relative situation and for non-Archimedean, again, you can try. So personally, I mean, me and my team, we work over finite field case, but yeah, so probably it is doable. Yeah. Again, I would be interested to look into it for sure. Yeah.
More questions? Well, if not, let's thank Sergey again.
Thank you very much.